Hello, it's Keith here, and this is lesson 65 of the platform-specific series of my 6502 assembly programming tutorials. We're looking at the BBC today, and what we've done here is we've added music to the min-tile example, the graphics example. Now, I should be able to move the character around the screen, but the joystick isn't detecting for some strange reason. That's the joys of working on two PCs. I use a different machine for my development, and the emulator works on that one and not on this one. Anyway, it doesn't matter because this isn't a joystick example, so I'm not going to waste my time configuring it. What we are looking at today is we are using the interrupt handler to drive the music, and that means that however slow our game gets, the music will play at the same speed, which is generally essential for music. There's going to be very rare times when it would be acceptable for the speed of the music to change when the gameplay got more complicated. Now, the 6502 processor will typically execute some memory address, the address at the very high memory addresses when an interrupt occurs, and so typically we would maybe assume that the FFFE to FFFF range will contain the address of our interrupt handler. That is sort of true. It's true that that is the interrupt handler address, however that is a ROM address. The BBC ROM will actually be executed by that address, and so we have to patch into the ROM's interrupt handler. Now, what we actually have to do is we have to put the address of our interrupt handler at the address 0204 and 0205 16-bit address, and that will actually be executed as part of the interrupt handling of the firmware. There are a couple of other addresses that are used. There's a different address for the break interrupt if the break flag is set, and also there's one for what's known as an unrecognized IRQ at 026 and 027. However, I don't believe we're actually going to need to take control of that. And then finally, there is one other kind of interrupt, the non-maskable interrupt, actually causes a full-on execution to memory address D00. Now, these are all vectors, meaning that we just have to put a 16-bit address at these addresses, and so we don't need to put any code here apart from the 2 bytes pointing to our actual address that we want to execute. But the D00 address is different, and that actually is a full-on jump to that address. Now, the operating system during the reset will actually put an RTI command at this address, but for our purposes this never gets executed anyway, so it doesn't matter. It's just referring to how these actually work. I thought it was important to sort of point out that that one was different. Now, I checked the official documentation with regards to how these work, and I also checked the disassembly of the source code of the operating system just to make sure I understood how everything worked. Now, with all of these, our interrupt handlers will have to work with the various registers. We'll have to back up parts of the 0 page for our sound driving, our sound routine. I'm using my ChibiTracks music player and Chibi Sound Pro that do the music for today's example. They use parts of the 0 page. We also need to back up the registers, and the accumulator is a bit of a special case. Now, the firmware interrupt handler has already used the accumulator. It needs to use it to check the break flag, and so it actually stores the accumulator at the 0 page entry FC, and so that is something we'll need to bear in mind when it comes to our routine, because we are now hijacking the interrupt sequence, and so when we return back to the calling routine, we will need to restore the accumulator to its correct value. We don't need to worry about the flags. They're backed up by the interrupt handling routines of the 6502 automatically. Anyway, enough talk. Let's go over to our source code and let's check out what we've got today. So this is the source file we're looking at today. The previous min-tile example, now with sound added. Our sound is being handled primarily by an interrupt routine. We have this interrupt handler here that is going to take over from the firmware and do the jobs that we require. Now, the first thing we're going to check is we're going to check what kind of interrupt has occurred. We only want to execute during the VBlank interrupts. Now, if I disable the check here, I've actually disabled that check for what kind of interrupt has occurred, and if I run again, well, we will find our music plays far too fast. That is because we are responding to interrupts that are nothing to do with what we actually want. We just want the VBlank interrupt, and that is the bit 1 here, and so we're testing that bit there. We're loading in from FE4D. This is the interrupt flags, and this marks which interrupt has actually occurred. So we're only looking for the VBlank interrupt, and for any other one, we will skip over to interrupt abort. Interrupt abort is down here, and what we're doing is we are writing the value 255 to FE4D. This clears all of the interrupts, so whatever interrupt occurred, this will clear it. And then we are loading back the accumulator from FC, because remember, the firmware has backed up the accumulator to the memory address FC in the 0 page. So here we're just restoring the accumulator. We're using the RTI command, which automatically restores the flags, so we don't need to use PHP PLP to back up and restore the flags. That's being done by the RTI command and the firmware functions themselves. Okay, now in the case that we get to this point, because we've done this check here, we are now using a VBlank interrupt. So we're going to run the ChibiTracks play. Now ChibiTracks is my music player, and the play routine updates the current sound that's being made. We need to back up some registers though. We need to back up the X and Y registers here for the ChibiTracks. We also need to back up some zero page entries. These mimic the Z80 registers. So there is a pair marked as HL, D, E, B, C and IX in the zero page. So this is a total of 8 zero page entries here. And I have a function called push pair, which automatically just pushes these onto the stack. So that's what's going on here. These are just being pushed onto the stack here and restored from the stack here. Say the zero page entries that have just been given the names H, L, D, E, B, C and IX, and these are the 16-bit pairs here. And these are all used by ChibiTracks. So that is our interrupt handler. I've put a little breakdown of all the bits within the FE4D entry there. As I say, we are using it here to test the current interrupt and using it here to clear the interrupt. So that is what they all do. As I say, the only final thing to remember is how we work with the accumulator. The firmware interrupt handler routine does not back up X and Y for us, so we need to do that ourselves. Okay, so that's our interrupt handler. How do we actually use it? Well, as I say, we can't use the default vectors of the 6502. They would be FFFE and FFFF. Those are going to call the firmware. They have to because we've got ROM in the high area. So we're going to hijack in there. And what they will do is they will jump to the address at memory address 204 and 205. So what we're doing here is we're loading the address of our interrupt handler and writing that address to this pair here, 204 and 205. And when we do that, the firmware interrupt handler in the BIOS, that will execute our interrupt handler as part of its normal execution. And that means that we will hook in and take control and be able to do the things we need. The only final thing there to do is clear the interrupts, and that will clear the interrupt flag, and that will enable interrupts and allow the music to play. Okay, so very straightforward there. So how do we actually use the ChibiTracks software, the music software that I wrote? Well, there's a couple of things we need. Firstly, we need to include all of the assembly files for ChibiTracks. There's ChibiTracks itself, Fraction 16 and the Tweener. Those are for the in-between notes. Those are some calculation routines. And ChibiSound Pro is the platform-specific sound driver. ChibiTracks is multi-platform. It's common to all 6502 systems, but the ChibiSound Pro is specific to the BBC. So that's what we need. We also, of course, need a song. We need something to play. This is a binary file. ChibiTracks can also use ASM files. That is the native format of the ChibiTracker software I wrote. It actually creates music files as ASMs so that you can see the contents of them, and if you want to assemble them directly in a Z80 assembler, but in this case we are using a binary file. Now, ChibiTracks and ChibiSound, they need some memory, so we need to allocate about 128 bytes here. We're specifying a memory address here that's some free memory. And then what we've got here is we are just defining the variables of the player in that memory block. Some of the memory, the first 64 bytes or so, will actually be used by the player itself for the channel statuses. But what we're doing here is we're moving to some free memory here. And we're going to use those for the various variables of the player. We are also enabling some functions here, some options that are entirely up to us if we want them. Allow relocation, I would strongly suggest you use. When you export a binary file from ChibiTracks, you specify the memory address that it's going to be loaded into, and this is used in the calculation of the pointers to the instruments and the play sequence and the patterns and things within the file. But suppose that's not the final address that you want to load to, well, that's going to be a problem unless you enable allow relocation. It adds a little bit of extra memory to the player, but not very much. I would strongly suggest it's worth you doing. Another one that is possibly more optional is allow speed change. This allows the playback speed to be changed at playtime. Otherwise, what you need to do is, if you disable this, you need to actually pre-multiply the speed. If you've got a speed of 5, what this means is the line speeds for each of the lines of the pattern will be multiplied by 5, slowing it down. But you can pre-multiply this, and then you can disable this function. That allows the player to be faster and smaller at playtime, but it removes the option of controlling the speed, which you might want to do if you've got a song that's being played at 50 and 60 Hertz on different systems. If I disable this option, because the file that I have today, it hasn't got pre-multiplied speed, the speed multiplication will no longer work. And you can hear it's playing extremely fast. So for today's file, because I didn't pre-multiply the speed, I really need to enable allow speed change. But if I had, then I could disable it. Now, that's how setting up the memory and loading in the various assembly files we need. How about actually starting the song? Well, we need to run Chibi Sound Pro init. This does the platform-specific sound setup for the hardware. We then need to load the address of the song we want to play. And then we need to run ChibiTracks start song. I don't think we actually need these. These were probably just for some testing. They will be set automatically by the actual play routines here, by the actual start song in its current form. So we don't actually need those. And then all we need to do after that is just actually update the song every time during our interrupts, if we're using interrupts. If we aren't, then we would need some kind of delay loop, but that would be far cruder. When we've got interrupts, we definitely don't want to do that. We just want to let the interrupts define when the song is being played. Now, as I say, if we enable that speed thing, we can actually change the speed in real time just by changing the song speed entry here. So here I'm setting it to 10, which is much lower than it should be. And if I run again, this will basically play the song at half speed. So you can hear it's playing far too slow here. Now, as I say, you might want a speed of about 6 or 7 if you were using a 60 Hz system. Also, if you were playing a game like Super Mario where the song speeds up as the player runs out of time, you might want a speed of something like 3 there, and that would give an increase in the speed, but it would still sound like the same song. Possibly a little fast, but as I say, you can see there that we have some options there. So there we go. That's all we're covering today. So you can go to my website, download the source code, the build scripts. As always, you can download today's example, and you can download ChibiTracks, Chibi Sound Pro, and the tracker. They're all free. So you're welcome to use them in anything you want. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.